In this video, I'm going to be explaining what the extreme value theorem is and what extrema are. The extreme value theorem simply states that if a function is continuous on an interval, there must exist at least a minimum value and a maximum value. So in this example, we can see that we have a continuous function between a and b, and there is a height here that is higher than everything else. That would be a maximum, and a low point here that's lower than everything else. That would be our minimum value. Extreme value theorem does not say that we have to have both. We could have more, but we have to have at least a maximum or a minimum. There are some exceptions though. A constant function is going to stay flat. It's never going to increase or decrease, so we don't have a maximum or minimum. Other functions that grow without bound, for instance, 1 over x is an example where this function on the left here is continuous, but it's going to decrease forever, and we can't establish a minimum value. And on the right side, even though it's continuous, it's increasing forever, and we can't establish a maximum value. So there are exceptions. Extrema is just a fancy word for minimums and maximums. Minima is the plural form of minimums, and maxima is the plural form of maximums. And together they're classified as extrema or extreme values. There's two different types. There's an absolute type, and that would be the lowest point on an interval. That would be the absolute minimum, and the highest point on an interval would be the absolute maximum. In between that, we might have little hills or valleys, and we classify those as what is called relative or local extrema. So if we zoom in on the spot, it may appear to be the lowest point on our graph until we zoom out and realize that it was just relative to that spot. The extreme values are going to occur at critical points, and horizontal tangent lines are going to occur at our maximums or minimums. So we can use that to determine where these are happening. However, the extreme value theorem does not tell us whether it's a maximum or a minimum. It just simply says that it exists somewhere on the interval. So we have to use the following steps to determine what type it is, whether it's a maximum or a minimum. Because we're dealing with critical points or critical values or places where horizontal tangent lines occur, we're going to be dealing with derivatives. So the first thing we need to do is find the derivative of a function. Then we can set the derivative equal to 0 and find zeros of the function, or find values where the derivative is undefined. And if we can establish where those are happening, what x values those are occurring at, we can plug those x values into the original function and evaluate the function to get the output, and then compare the outputs, figure out which one is bigger, which one is smaller, and classify them as maximums or minimums. For absolute extrema, we're also going to have to do an extra step and evaluate the endpoints as well, because as you can see in this example, sometimes those absolute extrema happen right at the endpoint, so we're going to have to test those as well. Let's do an example. Here we got the function negative x squared plus 2x. We're going to find the derivative first by using our power rule, and we get the derivative as negative 2x plus 2. We're going to set that equal to 0 and solve. So if we subtract 2 and divide by negative 2, we get a solution x equals 1. So the extrema is happening when x equals 1. We just got to figure out what type it is. So we're going to plug that value back into the original to figure out what the output is at that x value. When I plug 1 into my original function, I get 1 out. So I know that my extrema is happening at 1, 1. Later on, we're going to be doing what's called the first derivative test to establish whether it's a maximum or a minimum. But in this video, we're just going to be looking at the graph or determining function types to figure out whether it's a maximum or minimum. So I know that my original function was a quadratic, so it's going to have a parabola shape. I also know that the a value is negative, meaning that my parabola is going to open downward or be concave down. So I know that I'm going to have a maximum value. My function is going to go up and stop going up at some point and come back down. So it's got a maximum. So we knew that the horizontal tangent line occurred when x equaled 1, and we knew that our output was 1, so our maximum value has to be 1 for this function. Because our parabola is opening downward, We have a maximum, but we don't have a minimum because those parabola arms are going to continue going downward forever. Here's another example. Negative t cubed plus t squared minus 2, so a decreasing cube function. If we find the derivative using a power rule, we get negative 3t squared plus 2t. We can set that equal to 0 and solve. We can solve it by factoring a t out of both terms. We know that the zeros are going to be at t equals 0 and at positive 2/3. So two places where we have extreme happening. Let's figure out which is which. If I plug 0 into my original function, I get an output of negative 2. And if I plug 2/3 into my original function, I get an output of negative 50/27. So negative 50/27 is actually slightly more positive than negative 2, although not much. So negative 2 is going to be my lowest value. It's going to be my relative minimum. And negative 50/27 is going to be my relative maximum. And we can look at the graph to verify. So this is the graph of the original function, that decreasing cube function. We can see that we have a little valley right here at x equals 0. We know that's our relative minimum. And then just to the right of that, we have this little hill. That's going to be where x equals 2/3 and is our relative maximum. We can also do this with trig functions. So if I have a function sine of x, given the domain where our input or angle measure has to be in between 0 and 2 pi, we can try and figure out where we have extreme values. So the derivative of sine is cosine. If I set that equal to 0, I can figure out what angle measures give me a cosine of 0. So on this domain, I know that cosine is going to be 0 at pi over 2 and 3 pi over 2. If I plug those into my original function, I can get the outputs and compare them to figure out which is a maximum and a minimum. So the sine of pi over 2 is 1, and the sine of 3 pi over 2 is negative 1. So negative 1 is going to be my relative minimum value, and positive 1 is going to be my relative maximum value. And we can look at the graph to verify. At x equals pi over 2, approximately right here, we have a horizontal tangent line occurring at a hill. That'll be my relative maximum. And over here at 3 pi over 2 on the x-axis, I have a little valley, and that is representing my relative minimum. One more example. Let's focus on absolute extrema. So we're going to have to make sure and test those endpoints to make sure that extrema are happening or not happening at those values as well as our critical values. So again, we're given a function. We'll find the derivative first. The derivative of this function is 3r squared minus 4r. We can set it equal to 0. And it's quadratic again, so we can factor the quadratic and find zeros. If we factor an r out, then we find our zeros occur at r equals 0 and at positive 4/3. So I'm going to plug those values back into my original function and evaluate to get the output values. And I'm also going to plug my endpoint values into my original function and check to see what those outputs are. So I have 4 values that I'm checking, and I'm going to compare all of their outputs. So when I plug in negative 1, I get 0. When I plug in 0, I get 3. When I plug in 1, I get 2. And when I plug in 4/3, I get 49/27. So comparing all those values, the lowest value is 0. That's going to be my relative minimum. And positive 3 is going to be my biggest value. That's going to be my relative maximum. We can look at the graph of the original function given that interval and compare and verify. So when x equals 0, I do have a relative maximum. And when x equals negative 1, that's the end point of my interval. And that's actually the lowest point on my function in this interval between negative 1 and 1. So the end point ended up being where my minimum, absolute minimum, happened. So I got an absolute minimum, a relative maximum, and there are the extrema for that graph.